Hi everyone. So this is lesson 1.3. It's going to build on our last lesson on lines and angles, and it's going to talk specifically about triangles. Okay, so triangles are very important all throughout engineering. You'll see them on structural elements when you're looking at trusses. If you talk about triangulation and surveying and navigation, you'll also see the shape of a triangle and concepts of triangles used there. Okay, so it's one of the shapes that's known to be very strong. And there's several different types that exist. Okay, the most popular one that you're probably going to see is the first one here, okay, which is a right angle triangle. We have a specific section in this lesson just talking about that triangle. Then we have three other types that look at specific angles. Okay, a scalene triangle has three sides that are not equal. Okay, and correspondingly, their angles are all different as well. Isosceles triangles have two equal sides, okay, and two equal angles. They do not have to be 40 degrees. Okay, they could be 50, they could be 30. But two of the three interior angles of an isosceles triangle are the same. The last triangle, one that you see probably less often, is an equilateral triangle. In that case, everything matches. The three sides are the same size, and correspondingly, the three interior angles are all the same. Regardless of which of these triangles you have, one rule that always applies is all three interior angles of a triangle must add up to 180 degrees. Okay, in all four of these instances of different types of triangles, they have to add up to 180 degrees. Okay. In addition to talking about angles, there's three other scenarios, and these are all about looking at specifics when it comes to triangles. The first item I want to talk about is if you were to actually draw a line from each vertex, okay, each of these points on a triangle where two lines connect are known as vertices for plural, or vertex for a single one. If you were to draw a line that connects in the midpoint of every one of these lines, okay? And when I say midpoint, I mean this distance and this distance are the same. So it's exactly in half for each line. The corresponding center point here is known as the centroid. And what that is the center of mass. So if you were to machine that object yourself, okay, and you were to draw that, or you were to figure out where that centroid is, if you put your finger underneath that piece and hold it there, that's the center of mass. So that piece would actually stay sitting there because that is the center point where the mass not radiates out, but it is kind of the center of gravity. So it would hold it kind of in place there, okay? The second item I want to talk about is if you draw lines, but instead it splits the angles in half, okay? So these two angles are the same, these two angles are the same, and these two angles are the same, okay? The corresponding point is not the bisector, okay? But it shows, okay, as a different center point, okay, than the centroid, okay? And they meet at a common point, okay? Each of these lines is known as an angle bisector. The third one, and the one that you'll see probably used most often for you, is if you drew a line from each of the vertices to a point where the line was perpendicular to the connecting line on the triangle, so every one of them makes a 90-degree angle. Those are known as altitudes. So you'll see in our next discussion, we're going to talk about perimeter and area. These altitudes are very important when we talk about the basic formula for calculating area. Okay. Again, the point that these meet is not the centroid. It's only the centroid, or the center of mass, when the line splits each of the corresponding triangles lines in half. Okay, they all meet at a point, just each of those points is different. Okay, so I show you these just to make sure you understand these terms. All right, and we will use them or some of them more than others in future areas of this lesson. First of all, okay, going back, I want to classify each of these triangles according to the data provided for the triangle below. So in other words, based on the angles provided. Okay, angles and in some cases dimensions of sides. So triangle A, okay, it has an 84-degree angle and a 40-degree angle. Okay, so they're different. The third angle then must be, okay, so in other words, angle CAB must be equal to 180 degrees, the starting point, okay, because remember all angles in a triangle have to be 180 degrees, minus the other two angles, 84 degrees minus 40 degrees. And if we do that, okay, we get 56 degrees. I almost wrote 46. Okay, so that means that all the angles are different, and correspondingly, all of the sides would then also be different, right? Because no angle is the same. So that means this must be a scalene triangle. For B, okay, immediately I can tell what it is because it has a right angle, okay? As soon as you see that square and you know it's a right angle, that's a right angle triangle. For C, okay, similarly, we see that we have two sides that are the same, okay? So that means that this angle must also be the same, and this must be an isosceles triangle. And the same thing goes, for example, D, okay? The two sides are the same. Just because you're given 110 degrees, you could calculate the other two angles, but we don't need to because all we are doing is classifying the triangle. And in this case, again, because two sides are the same, it is an isosceles triangle. We don't need the data that shows that the angles are the same in either of these cases, because that is one of the principles of triangles. If two sides are the same, and automatically those angles will also be the same. Okay, it's a property of an isosceles triangle. So now that we've classified triangles and we've looked at some of the specifics, altitude being the most important one that we're going to talk about in this slide. Some other properties of triangles include the perimeter, which is a basic calculation, okay, the sum of all the sides. So if you have a triangle like this with sides of length A, B, and C, the perimeter is simply the sum of those three side lengths, A plus B plus C. The area is a little bit different, okay, because when you're calculating it, you have to know the height of the triangle, okay? And remember, when we calculated altitudes, okay, they were a 90-degree angle from that line, okay? So in this case, the area is 1/2 multiplied by the base, or in other words, the bottom line of the triangle, multiplied by the height. So the height being from this base line up to the vertex, and it has to be at a 90-degree angle. It has to be, okay? Because that height has to be straight up and down, okay? Alternatively, you could flip this triangle, okay? So all I did was flip it, and you can take any one of these, okay? Sorry. You can take any one of these and find a point that's at 90 degrees. Okay, so it doesn't just have to be this side that you're provided, but usually it will be the bottom side that's given as the base. Okay, that's term B. And the height is the altitude, in other words, straight up and down. Okay, so that is kind of the first way to find the area. We'll get into another method in another slide. So using these formulas, we're just going to do a basic example. Find the perimeter and area of the following triangle. Okay, so remember, perimeter is the sum of the sides. We call them A plus B plus C. Okay, so the perimeter is simply 9 centimeters plus 13.65 centimeters plus 17 centimeters. And if we do that, we get 39.65 centimeters. Now in this question, area, we know the height, right? In other words, one of these altitudes is given as 7.2 centimeters. So the area is 1/2 times the base times the height. In this case, it's 1/2 times the base, in other words, the bottom piece, 17 centimeters, multiplied by the height. Okay, again, this altitude was given 7.2 centimeters. Okay? If you multiply that out, you get 61.2, and it's centimeters squared, right? Because it's centimeters multiplied by centimeters. Okay? So using that basic formula is nice when you know the height. But what if you can just measure all the different sides? Okay? This might be common, especially if you're doing something, or if you have a triangle and you're doing woodworking and maybe you can't measure that height, but you can measure the sides. You can think about the sides. So there is actually a mathematician that came up with Hero's formula. Okay? I put his sketch here. His name's Hero or Heron, as he was known. Okay? And this formula uses a concept known as S. Okay, so we kept the same items, A, B, and C, which are just the lengths of each of the sides. It does not have to be a right-angled triangle. I'm showing it as a right-angled triangle, just I find them easiest to show graphically. But the other concept is S. Okay, and what S is half of your perimeter. Okay, remember your perimeter was the sum, A plus B plus C. So S is simply 1/2 of A plus B plus C, okay? So using this formula and multiplying these together, so it's S, or the half perimeter, multiplied by the difference between that half perimeter and each side. So S minus A times S minus B times S minus C. And all of that is then you take the square root of, okay? So let's look at an example of that. Find the perimeter and area of the following triangle using Hero's formula. Okay, so perimeter, pretty straightforward, A plus B plus C. Okay, 9, and I'll leave centimeters. So 9 centimeters plus 16 centimeters plus 21 centimeters. And if you do that, you get 46 centimeters. Now the area, we don't have an altitude. We don't have this value. Okay, we don't know what it is, but we do know all the sides. So we can use the area is equal to the square root of S times S minus A, S minus B, and S minus C. And remember, all of that is then you take the square root of that final answer within the square root. Okay? So S is equal to 1/2 of A plus B plus C, which is equal to 1/2 of 9 centimeters plus 16 centimeters plus 21 centimeters. You could also have just substituted in the 46 centimeters here, knowing that A plus B plus C was the perimeter. Again, totally up to you. If you do that, you get 1/2 of 46 centimeters, which gives you 23 centimeters. Okay? Now, if you calculate this out, your area is equal to your square root of 23 centimeters times 23 centimeters minus, you can pick any side for A, B, and C. It doesn't matter. Okay, so I'm just going to pick A as the same as I did up top, 9 centimeters, times 23 centimeters minus B, which is 16 centimeters, times 23 centimeters minus 21 centimeters. Okay, and then the square root of all of that. And if you do this, you'll get the square root of 23 centimeters times 14 centimeters times 7 centimeters times 2 centimeters. Okay? Again, multiplying that out, you get the area is equal to the square root of 4,508. And keep in mind, we have centimeters times centimeters times centimeters times centimeters, which is actually centimeters to the exponent 4. You'll see why that's important when we take the square root. Okay? So if you take the square root, okay, if you remember this, you're actually taking this 4,508 centimeters to the exponent 4 to the exponent 1/2. Okay? Either way, I'm just showing you this to show how the units actually work out. So if you take the square root of 4,508, you get 67.14. And then the second term is centimeters to the exponent 4. And again, because it's square root, it's the exponent 1/2. So if you have that, remember from exponents, you multiply those two exponents together. So what happens is that's 67.14 centimeters, and that's 4 times 1 divided by 2, which gives you 67.14 centimeters squared. Okay? I don't expect you to show that level of detail to show how those units work in these types of cases. I'm just showing you that so you understand that this formula will still give you square centimeters or whatever units might be in, square millimeters, square inches, square meters, okay? Just showing you how the units work, okay? So using this formula, that is the area you would obtain. Now, if you still have questions on the last example that I just did where I found and converted and showed you how it became centimeters squared, keep in mind I am going to go through exponents later on in this course. For some of you, you may have seen those rules I applied already. If not, don't worry. That's just a preview of what you'll see further on in the course. Okay? If you simply use your square root button for that number in the previous example, you'll get the right solution. So the next number I want to talk about is Pythagorean Theorem. Okay? And that really was made popular by this guy, okay? Pythagoras. And this relates specifically to right-angled triangles. Again, you'll notice in this case, I've used the same kind of image all the way through, but the important thing on a right angle triangle is one angle has this square showing. Okay, that's denoting that it has a 90-degree angle and is a right angle triangle. So what this is it shows you a way to figure out a third side if you already know two of them, whether you know the long side, which is known as the hypotenuse, C, or if you know one of the shorter sides, A or B. And this formula is very simple. It's C squared equals A squared plus B squared. In other words, the long side, known as the hypotenuse squared, is equal to the sum of the squares of the two shorter sides. Okay? It's a very important theorem to know. I find right-angled triangles to be one of the most useful items to know when it comes to looking at geometry because there's so much you can do with it. If any of you, outside of your work might get into something like woodworking, right angles become very important in everything from furniture making and cabinet building, even just making simple items. If you don't have the proper right angles, then things won't come together properly. Okay? So let's look at an example using this formula. Find the length of side C for the triangle shown below. Okay, so in this case, we're given two sides, the two short sides, and the side that's on an angle, the long side, is always known as the hypotenuse C. Okay, so we start with our formula, C squared equals A squared plus B squared. Okay, the side C squared is always the hypotenuse. So the side of the equation that only has one variable is always where you would place the hypotenuse. And we don't know the hypotenuse here. Okay? What we do know is the other two sides. So C squared has to be equal to A squared, 10, plus B squared, 25. So if you calculate that out, you get C squared is equal to 100 plus 625, or 725. So in order to solve that, all right, because it's squared, we have to take the square root of it to get just C by itself. So C is equal to the square root of 725. Okay, so if you use the square root button on your calculator, square root of 725, you end up getting an answer of 26.9 centimeters. Okay, and again, you have to think and do a fact check here when you're looking at, especially when you're calculating a hypotenuse. That number you obtain, 26.9 centimeters, always has to be larger than the other two. The hypotenuse is always the longest side. So if you get something that's less than, let's say, 25, let's say this was 24, you know that that's wrong. Okay, it has to be larger because it is, the hypotenuse is the largest side in a right angled triangle. Okay, so let's look at a little more practical of an example. An observer is 550 meters horizontally from the launch pad of a rocket. After the rocket has ascended 750 meters vertically, how far is it from the observer? So, I'm not the greatest at drawing symbols, but we'll draw a rocket, okay? And it's ascending upwards, okay? And you're sitting somewhere over here, okay? That's a bad person that I just drew, but nonetheless, you know that you are 550 meters away, and the rocket has ascended, I should show this so it's more to scale, 750 meters. So what you're trying to figure out is how far away are you? So the most direct way to calculate that is to find a line between those two. And what that does is it makes a triangle. Okay? And since your 550 meters is directly horizontal, and the rocket we're assuming is ascending directly vertical, those two lines must be perpendicular, meaning this angle must be 90 degrees. So we have a right-angled triangle. So that means we can use Pythagorean Theorem. C squared is equal to A squared plus B squared. So we don't know C, we don't know the hypotenuse. That's what we're trying to find. So C squared is equal to 550 squared plus 750 squared. In other words, the length of your other two sides. Okay? So if you calculate those, you get C squared is equal to 865,000. So to get C on its own, again, because it's squared, you take the square root. So C is equal to the square root of 865,000, which gives you a distance of 930 meters. Okay? So again, using the data in the question, you have to pull out those relevant bits and start to come up with a sketch that explains kind of what we're looking at. Once you get to that point and you figure out the formula to use, you can see the formula is pretty straightforward, right? It's getting all of this data sorted out first to make it easier for you, okay? The last concept I want to talk about, okay, we talked about different types of triangles, we've talked about different points, including altitudes, areas, and perimeters. Now I want to talk about a concept called similar triangles. Okay, so similar triangles are triangles that have the same shape, but not necessarily the same size. Okay, so in other words, one might be scaled up and larger than the other one. Okay, in order to be similar triangles, their angles measurements are the same. Okay, they do not have to be right-angled triangles like it looks like, but their three angles have to all be the same. Okay, so they can all have, let's say, 60, 30, and 90, because that equals 180. But they have to have the same three angle numbers, and the sides of them have to be proportional. Okay? And what I mean by proportional, right, is these have to all, be proportional in terms of their lengths and widths. When they have the same angles, they typically will end up being proportional. And when they are, remember, back to our first lesson on proportions, then what that means is the sides are all proportional to one another. Okay? So in other words, side AB, in this instance is the long side. I'll switch to red so you can see it a little better. So side AB divided by side A, and I'm calling them A prime and B prime. Okay, in other words, that same side on both triangles, that ratio has to be equal to the ratio of the next side, BC, divided by B prime and C prime, which has to be equal to the last side, the ratio of those two sides, AC divided by A prime and C prime. Okay? It can allow you to figure out, for instance, if you had a small triangle or a small item and you were looking at scaling it up, again, I can use an example of woodworking. You can use similar triangles in order to know what the new dimensions of the new larger triangle would be. Okay? So let's look at an example. A water pumping station is to be built on a river at point P in order to deliver water to points A and B. Refer to the figure below. The design requires that angle APD is equal to angle BPC. So find the lengths of pipe CP and PD. Okay? So you know that those angles, these corresponding angles, okay, APD and BPC, okay, have to be equal. Okay? So what that means is in this case, it doesn't show it, but you can assume that these are going straight up and these are 90 degrees. So that means all the interior angle measurements are going to be the same. So these are similar triangles. Okay? So we can actually figure out, what we're trying to figure out is what these lengths are. So CP and PD. Okay? So what we know is that from similar triangles, this length AD divided by this length BC has to be equal to this line PD divided by this line, we'll call it CP, okay? Because they're similar triangles, all right? The other item that we know is we know the total distance, okay? So we know this total distance is 12 kilometers. And there's two triangles as part of that. So it means the length CP plus the length PD has to be equal to 12 kilometers, right? Because that's the total distance from point C to point D. P is just an intermediate point, okay, in the middle. So we can start substituting some of our values in. So line AD is 10 kilometers divided by line BC, which is 6 kilometers. And that has to be equal to PD divided by CP. So we haven't covered this piece specifically, okay? You've seen it in the past. But now we have two equations and we have two items that are unknown. So what I'm going to do is I'm going to solve this proportion for PD, so I can substitute it into the equation here. Okay? So to do that, I have to have PD on its own. So I multiply both sides by the line CP. And now because it's in the numerator and the denominator, it cancels on this side. And what you're left with is 10 divided by 6 times CP is equal to PD. So now since that's equal to this term, I can simply substitute it in. So now, going to my second equation, I have CP, again these are the lines, plus 10 divided by 6 times CP, which is equal to 12. So using equivalent fractions, okay, so CP can also be written as 6 divided by 6 times CP, because I'm trying to find the lowest common denominator here. Okay, so 6 divided by 6 is just 1, so it's the same as just writing CP, plus 10 over 6, CP is equal to 12. So you can do it with fractions, or, to be honest, the way I will probably see a lot of you do it instead of this, so I was going to show you, I'll just show you that way in case you choose to, is to just add them up. So 1 plus 10 divided by 6. And you end up with 2.67 times CP is equal to 12. And all I did was add 10 over 6 times the 1 that actually would be here, since it's just times CP. Now solving for CP, I'm going to divide both sides by 2.67. And we figure out that CP is actually 4.5 kilometers. What that means is we can now solve for PD. So going back to our original equation, 4.5 plus PD has to equal 12. So to solve for line PD, we subtract 4.5 from both sides. So in this case, negative 4.5 plus 4.5 cancels, and we're left with PD is equal to 7.5 kilometers. Okay? So we kind of used a combination of two items, okay? We used similar triangles in order to find that relationship between these two variables. And then we simply knew the total distance, right? And we know that this point has to be somewhere in between. So the point was where is it? Okay? So that was all I had for triangles. Okay, again, I have picked these questions just based on what we've covered. If you have questions, please feel free to send me an email or ask me questions during tutorial sessions. I'm always happy to answer your questions as best I can. So thanks, everybody.